Welcome to the tutorial series on network analysis made simple. During the previous tutorials, we discussed about the different techniques of network solving such as branch current method, mesh current method, node voltage method, super node concept, super mesh concept and so on. In this tutorial, we shall study the maximum power transfer theorem part 1 taking networks containing pure resistance load varying. Friends, let me tell you why we need to study maximum power transfer theorem. Look, in electric circuits, the loads receive electrical energy via supply sources. Power transfer is a continuous process and power or energy is precious. So, from any source of power, how much power is transferred to load? What is the power transfer efficiency? These aspects are the concerns of the circuit designers. But then, some logical questions arise, such as can we design the circuit to transfer maximum power across the load? And what could be the load impedance that it has to have for maximum power transfer? This is an important issue in many practical situations. Friends, now let us take up a very simple circuit consisting of a source and a load as shown in figure. A source of Vs volts with an internal resistance of Rs ohm is connected across a load resistance of RL. Can you recognize Thevenin's equivalent circuit in this figure? Yes, friends. If we take Vs is equal to V Thevenin and Rs is equal to R Thevenin, we see the Thevenin's equivalent circuit. Then, you may be thinking why this circuit is chosen. I have an answer, friends. You know that given any circuit having number of sources and linear circuit elements, we can get its Thevenin's equivalent circuit across the load branch as shown. Now, we know in this circuit IL is equal to Vs divided by Rs plus RL, and power transfer to load resistance RL is, say, PL is equal to IL squared into RL watts. Now, let's find the equation for the power transfer efficiency. We know P in is equal to Vs into Is, and by substituting the values we get power input is equal to Vs squared divided by Rs plus RL watts. But power transfer to load, say P load is equal to IL squared into RL. By substituting the values, we get P load is equal to Vs squared divided by Rs plus RL whole square into RL. Hence, power transfer efficiency is equal to P out by P in, or it is equal to P load by P in. By substituting for P load and P in, we get percentage power transfer efficiency is equal to RL divided by Rs plus RL into 100. Friends, we are going to use this equation further in our discussion. Hence, you have to remember this equation. Now, let us see at what value of RL power transfer is maximum. For that, consider a simple circuit of 10 volts source having a source resistance of 5 ohm connected across a varying load resistance RL as shown. Let us assume that RL varies from 1 ohm to 10 ohm. For different values of RL, current IL and power across RLP calculated is shown in the table. By observing the power delivered you see that it goes on increasing from 1 ohm to 5 ohm, and after 5 ohm, even after you increase the load resistance, you find that the power delivered decreases. The graphical relation of RL versus P is shown aside. You see that power transfer is maximum at a particular value of RL, that is RL equal to 5 ohm. What does it mean? Look, output power is maximum when Rs is equal to RL, that is when the source resistance is equal to the load resistance. Friends, for every circuit we cannot follow this process of finding the value of load when power transferred across it is maximum. Further, the condition of the value of load depends on the type of source, that is whether the network is AC or DC, type of source impedance and the load impedance. We shall see these aspects in further discussion. Since the condition for the maximum power transfer depends upon the type of network, we shall categorize the networks into 5 groups. Case 1, when source is DC and load is pure resistance varying. Case 2, when the source is AC, source impedance is complex and pure resistance load is varying. Case 3, source is AC, source impedance is complex and the load impedance also is complex, but only RL is varying. Case 4, source is AC, source impedance is complex and the load impedance also is complex, but only XL is varying. Case 5, source is AC, source impedance is complex and the load impedance also is complex, and both RL and XL are varying, and we are required to find the conditions for all these cases. We shall see as and when we go further. Friends, if you observe the networks in all the cases, you see that at least one load component is varying. What does it mean? Remember, the maximum power transfer theorem is applicable only if any one or more load components are varying. Friends, first let us take case 1. In this case, the source is DC and the load is pure resistance varying as shown in figure. We know that IL is equal to Vs divided by Rs plus RL amperes, and P load is equal to IL squared into RL. Let P load is equal to P. By substituting the value of IL, we get P is equal to Vs squared into bracket RL divided by Rs plus RL whole square watts. To find the load resistance RL when maximum power is transferred across it, we have to find dP by dRL and equate dP by dRL to 0 and get the condition for maximum power transferred. Hence, dP by dRL is equal to d by dRL of Vs squared into RL divided by Rs plus RL whole square. Here Vs squared is constant and d by dRL of this is u by v form. Hence we know dP by dRL is equal to denominator into d by dRL of numerator minus numerator into d by dRL of denominator divided by denominator square. After finding dP by dRL and equate it to 0, we get Rs plus RL whole square into 1 minus RL into 2 into bracket Rs plus RL equal to 0. By rearranging it and solving it, we get RL is equal to Rs. Hence, when the source is DC and the load is pure resistance varying, the condition for maximum power transfer across it is RL is equal to Rs. Please remember this. By substituting RL is equal to Rs in the equation of power, we get P max is equal to Vs squared divided by 4RL watts. Friends, now let us take an example to find the value of load resistance RL for maximum power transferred across it. Also, we are required to find the maximum power transferred. Consider the given network shown in figure. It has two junction nodes, four branches, and note that all sources are independent sources. First, let us find VOC. To find VOC, we have to open the load branch as shown in figure. One way is to convert the independent current source into voltage source as shown and use mesh current method. Note that there is only one closed loop. Another way is to use node voltage method. Note that there is only one unknown V1. Friends, we can also use the node voltage method taking the original network as it is. Friends, I will solve the network taking the original circuit itself as it is. You can try other methods and solve, and you see that you must get the same answer. By writing the Kirchhoff's current equation for node 1, we get V1 minus 5 by 8 plus V1 by 4 minus 2 is equal to 0. Current in 4 by 3 ohm resistance is 0 as the terminals A and B are open. By solving for V1, we get V1 is equal to 7 volts. But you see that VOC is equal to V1 plus 1 and hence we get VOC is equal to 8 volts and Thevenin also is equal to 8 volts. Since all sources are independent sources, let us use procedure 1 to find R Thevenin. By making all sources 0 as shown in figure, we find that 8 ohm and 4 ohm are in parallel and this parallel combination is in series with 4 by 3 ohm. Hence, R Thevenin is equal to 8 into 4 divided by 8 plus 4 by 3 which will give us 4 ohm. We know that the source is DC and the load is varying resistance. Hence, condition for maximum power transfer is RL is equal to R Thevenin is equal to RS. Hence, RS is equal to 4 ohm and RL is equal to 4 ohm. And we also know that V Thevenin is equal to Vs is equal to 8 volts. By drawing the Thevenin's equivalent circuit across the load branch, we get the circuit as shown in figure. We know that P max is equal to Vs squared divided by 4RL and that is equal to 8 squared divided by 4 into 4 which will give us 4 watts. Friends, we know that Rs is equal to RL is equal to 4 ohm. And by substituting the values in the equation of power transfer efficiency, percentage power transfer efficiency is equal to RL divided by RS plus RL into 100. By solving it, we get percentage power transfer efficiency is equal to 50%. Friends, let us take another very interesting and typical example to find the load resistance for maximum power transferred across it and also find the maximum power transferred. We see that the network has 3 junction nodes, 5 branches. Observe that the network has both independent and dependent sources. To find VOC, let us see what different ways are available. One way is to use nodal voltage analysis using the given network itself as it is as shown in figure 2. Second and third method could be to convert the dependent current source and use either nodal analysis as shown in figure 3 or use mesh current analysis as shown in figure 4. Consider figure 2. There are 3 junction nodes 1, 2 and 3. Let V1 and V2 be the unknown voltages as assumed. Write Kirchhoff's current equation for node 1 and 2 and solve for V1 and V2. Note that VOC is equal to V2. Consider figure 3. Here there are only two junction nodes, hence assume Phi1 as unknown. Write Kirchhoff's current equation for node 1 and solve for Phi1. Note that VOC is equal to Phi1 minus 2 into I 2 ohm. Consider figure 4. There are two independent loops. Let I1 and I2 be the mesh currents assumed. Write Kirchhoff's voltage equation for both the loops and solve for I1 and I2 and get Vx also. Note that VOC is equal to 5 times Vx plus 10 I2. Friends, I will solve taking the original network as it is, that is figure 2, and you can solve by other methods and get the same answers. Let V1 and V2 be the unknown node voltages assumed as shown in figure. By writing the Kirchhoff's current equation for node 1, we get V1 minus 50 divided by 3 plus V1 by 6 plus V1 minus V2 by 2 is equal to 0. By solving and rearranging it, we get 6V1 minus 3V2 is equal to 100. Let it be equation 1. By writing the Kirchhoff's current equation for node 2, we get V2 minus V1 by 2 minus 0.5 Vx plus V2 by 10 is equal to 0. But we know Vx is equal to V1. Hence, by substituting for Vx, solving and rearranging it, we get minus 10 V1 plus 3 V2 is equal to 0. Let it be equation 2. By solving the balance equations 1 and 2, we get V1 is equal to 100 volts and V2 is equal to 166.67 volts or 500 by 3 volts. Therefore, VOC is equal to 500 divided by 3 volts. Friends, to find ISC, I will tell you how to solve it using mesh current analysis. Short the terminals A and B as shown in figure 2. The network has three independent loops. Assume mesh currents I1, I2 and I3 as independent variables. Write the Kirchhoff's voltage equations for loops 1, 2 and 3. Note that Vx is equal to 6 into bracket I1 minus I2. Solve the three simultaneous balance equations and get I1, I2 and I3. Note that ISC is equal to I3. To find RThevenin, use RThevenin is equal to VOC divided by ISC. Friends, you solve by this method which I have stated now, but I am going to introduce another very easy method of solving for RThevenin, and that is called as test source method. Friends, first let me tell you the procedure of solving for RThevenin using test source method. First of all, you should know that this method can be applied to any circuit situation. There are no restrictions at all. In this method, we have to connect what is called as test source as shown in figure. Let it be Vt equal to 1 volt. But all independent sources present in the network are to be made 0. And we know that to make voltage source 0, we have to short circuit it. To make the current source 0, we have to open circuit it. Hence, 50 volts independent voltage source is shorted as shown. After this, using suitable circuit solving technique, find IT. You know IT is the current delivered by the test source. Then find RThevenin using RThevenin is equal to Vt divided by IT. Friends, It is very simple, you know. To find R Thevenin, let us use nodal analysis. Let V1 and V2 be the unknown node voltages as shown in figure. By writing the Kirchhoff's current equation for node 1, we get V1 by 3 plus V1 by 6 plus V1 minus V2 by 2 is equal to 0. But we know Vt is equal to 1 volt and hence V2 is equal to 1 volt. By substituting V2 is equal to 1 volt, solving it, we get V1 is equal to 0.5 volts. Now, by writing the Kirchhoff's current equation for node 2, we get V2 minus V1 divided by 2 minus 0.5 Vx plus V2 by 10 minus It is equal to 0, or It is equal to V2 minus V1 by 2 minus 0.5 Vx plus V2 by 10. We know that V1 is equal to 0.5 volts, V2 is equal to 1 volt and Vx is equal to V1 is equal to 0.5 volts. Substituting and solving for It, we get It is equal to 0.1 ampere. Therefore, R Thevenin is equal to Vt divided by It and that is equal to 1 divided by 0.1, which will give us 10 ohm. Friends, is it not simple? Knowing Thevenin and R Thevenin, the Thevenin's equivalent circuit across the load branch is as shown in figure. We know that the given network is DC and the load is varying resistance. Hence, for maximum power transfer, RL is equal to R Thevenin and hence RL is equal to 10 ohm. We know that maximum power transferred P max is equal to Vs squared divided by 4 times RL, or P max is equal to V Thevenin square divided by 4 times RL. By substituting the values, we get P max is equal to 694.44 watts. Friends, in this tutorial on maximum power transfer theorem, we have learned to solve DC networks to find the load resistance RL for maximum power transfer across it. We also have learned a very easy method called test source method to find R Thevenin given any circuit situation. We also discussed different ways to tackle a single problem. This will help you to develop your thinking process. Hope this tutorial has ignited your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.